Let's start the new topic, angular momentum of a particle. Here you can see this figure which is of three-dimensional, and here I have put a particle of mass m. And it is having a position vector. You can clearly see this is origin O, and this position vector OQ is denoted by small r. Here if you want to find out the linear velocity of this particle, then I am consider over here that the linear velocity is small v. And with this linear velocity and this mass, I can obtain a new physical quantity, that is momentum of the particle. But here I am using the word, the linear momentum. See, till now I have only discussed the linear kind of motion. I have not observed the rotational motion from this point Q to point R. I am just consider at present the linear motion. And so, the linear momentum is denoted by small p vector, and that is given by the relation mv vector. Now, when this particle is rotating with respect to this angle theta, and this particle is rotating in which plane? See, this is x and y. So combinedly, this particle is moving or rotating in xy plane, with the angle theta. And so, now I can find out the angular momentum of this particle with respect to this center point, or we can say this reference point O. Now, the product of the position vector r and the momentum p is called the angular momentum of the particle. And this angular momentum is with respect to the reference point O, and it is rotating with the angle theta. Now, I can find out the value of angular momentum with this relation. See, this angular momentum is denoted by small l. So these symbols now you have to remember, and is given by r cross p. So this is the vector product of two vector quantities, means the cross product here I have taken. Now we will see some properties of this angular momentum. So the first property which I am going to discuss over here is of the magnitude of L. Now, the magnitude of L is depending on which quantities. So first of all, it depends on the selection of reference point. Because with the help of reference point, you are able to find out the angle, means theta, and this angle theta will make the change in the actual value of angular momentum. So this is the selection of reference point, and this reference point must be mentioned. Now the second one is the direction of angular momentum. That depends upon the right hand screw rule. Which you have used for the vector product, and in the present case or in the figure what you have seen, so the direction of L I am giving you. Such kind of arrangement. This is the reference point O. Here the x-axis, y and z-axis. Your position vector was OQ in this direction. So this is the value of position vector R. The direction of momentum was in this direction. So it is the direction of P, and here there was a point R. Now if you see the cross product of R cross P, so according to the right hand screw rule, the perpendicular direction will be taken, and hence in this direction the direction of angular momentum exists. So in our case, the direction of angular momentum is OZ vector. Similarly, if you want to find out the actual magnitude, then mod L or modulus L is given by modulus R cross P, that is equals to Rp sin theta. Now, here you consider one thing, that the component of vector R in the y direction, and that is OR, and that is the actual value of R sin theta. And so the magnitude of angular momentum L is P into R sin theta. See, I have just interchanged the terms of P sin theta and R. Here the value of P is as it is, and this OR vector, or we can say the OR component, is the y component of position vector small r. So the magnitude of L, means small l, is given by the value of linear momentum into the perpendicular distance of the vector of position. And so this is the actual representation. In another way, you can find out the value of R cross P by using the determinant. So for that, magnitude of L is equals to magnitude of R cross P, and we know the magnitude of R cross P is given by the determinant I cap, J cap, K cap. Here the position vector means x-axis, y-axis and z-axis, and the components of this linear momentum, that is Px, Py, Pz. So that is the determinant. And now, if you want to find out the value of this determinant, then you have to simplify it. So after simplifying, we will get I cap y into pz minus z into py plus j cap into x into pz minus z into px plus the remaining terms I am writing over here, that is k cap into xpy minus ypx. So, the angular momentum can be written as the vector sum of their component forms, that is equals to lxi cap plus lyj cap plus lz k cap. So actually the value of angular momentum L is depending upon the x component, y component and z components of the angular momentum. And with this we have find out the value of angular momentum for a particle. Now we will deduce some relations. Now, after studying the angular momentum of a particle, let's find out the relation between the angular momentum and the torque acting on it. So first of all, the angular momentum of a particle is given by vector L is equals to vector R cross vector P. So that is our equation 1 for this analysis. Now what I am doing, let's differentiate this equation with respect to time. So what we will get? Differentiating above equation with respect to time. Therefore, dl by dt. Now, as you know, the relation for differentiation in the multiplication, that is one quantity is constant, means outside the integration, into the differentiation of the remaining quantity plus now the other quantity will be constant, that means vector p, and the differentiation of the remaining one, that means dr by dt. But we know the rate of change of momentum with respect to time is given by force. So here I am denoting this particular quantity as the force, and also the rate of change of position with respect to time. So that is displacement upon time, and this is our velocity. And now my equation will look like, therefore dl by dt is equals to r cross f plus vector p cross vector v. But here if you see, the velocity and momentum both are in the same direction, and so their cross product will be 0. What is the reason behind that? The reason behind this is that both are in the same direction. and so this vector product will be 0. Now, after concluding that this quantity is 0, I can write down the value of dl by dt is equals to position vector r cross the force vector F. Now, if you remember, earlier we have discussed that the vector product of position vector and the force is given by torque. That means tau vector. And hence, if I write this equation jointly, then tau vector is equals to dl vector by dt. So this is the actual relation between the torque and the angular momentum of a particle. So I can write one statement from this equation number 2 as the time rate of change of angular momentum is equal to the torque. Also, if we move further, then this relation is similar to the Newton's second law of motion. The Newton's second law of motion was what? The rate of change of momentum with respect to time was force. And in linear motion, as the force plays the role in the motion study, similar way here the torque plays an important role in the rotational motion study. So, equation 2 is similar to Newton's second law of motion. And with this, our relation obtaination is over. Now, as we have studied the angular momentum on a particle, now we will see the effect of angular momentum on a system of particles.